Hi everyone, my name is Chen Zhou, and I'm a PhD student from the Hong Kong Polytechnic University. Today my topic is mechanisms for suppressing discontinuous precipitation and improving mechanical properties of nickel-aluminum strengthened steels through nanoscale copper partitioning. First, I will introduce the research background. High-strength steels play important roles in transportation, energy, aircraft, shipbuilding, construction, national security industries. Development of high-strength steels is technologically important because they allow for the design of the lightweight, cost-effective, and energy-efficient components. There are four strengthening methods often used in steels to strengthen steels, and they include solid solution strengthening, ground boundary strengthening, spring hardening, precipitation strengthening. Well, these methods are aiming at prohibiting the dislocation mobility. The precipitation strengthening is recognized as the most effective method to strengthen steels by introducing the second precipitates. Generally speaking, precipitates with a small particle size and high number density has allowed the development of advanced steels with high strength, high ductility, good weldability, and low cost. And this method is very easy to process because treatment process is very simple. And among various potential precipitates used for precipitation strengthening, nickel-aluminum is one of the most effective phases. Nickel-aluminum has a B2 outward structure with a lattice parameter close to that of BCCl. The high coherency results in a decreased interfacial energy for nucleation, thus the nucleation rate increases, leading to the formation of high number densities nanoparticles. And the nickel-aluminum has high outer energy, which can contribute to the high strengthening effect. And in precipitation strengthened steels, there are two precipitation modes, namely the continuous precipitation and the discontinuous precipitation. Continuous precipitation refers to the formation of spherical particles in the matrix, and discontinuous precipitation refers to the coarse rod-shaped precipitates formed along the ground boundaries, which grows into the grain interior results in the deep colonies. Well, the discontinuous precipitation is of great interest because it generally has a deleterious effect on the mechanical properties, such as it can cause poor ductility, poor stability, poor overaging resistance. So it is significant to understand how to control the DP reaction in the nickel-aluminum strengthened steels, and most studies focus on the CP reaction. Research on the DP reaction is very limited. In nickel-aluminum strengthened steel, how does the DP reaction proceed? We first check the microstructure evolution of our model steel. You can see from the SEM images, the bright contrast regions represent the DP region, while the dark contrast regions represent the CP region. With aging time, the area fraction of the DP regions increases significantly, reaching about 17% of the microstructure. But to deeply understand the characteristics of the discontinuous precipitates, we check with the atom probe tomography experiment work performed. From the atom maps and the isosurface of the precipitates, we can see that the discontinuous precipitates are rod-shaped and they are aligned parallel to each other, and the precipitate's radius is less than 10 nanometer. We use the EBST to deeply understand the growth of these deep colonies. As we can see from the left two fingers, the green boundary migrates from the right to left. And the right finger, the high magnification in the right part, we can see that the nano-sized Zhou-shaped precipitates are aligned normal to the migrated reaction front, advancing into the supersaturated matrix. And this kind of reaction has a close relationship with the green boundary characteristics. Well, how to suppress the discontinuous precipitation? We know that in supersaturated alloys, continuous and discontinuous precipitation occur competitively. So maybe we could use the continuous precipitation to suppress the discontinuous precipitation. And on the other hand, we can control the green boundary characteristics to control the occurrence of the DP reaction. Well, in nickel-aluminum steels, it was found that copper can influence the formation of continuous nickel-aluminum particles and form the co-precipitates with nickel-aluminum. But the effect of copper on the discontinuous nickel-aluminum precipitation is still elusive. So we add copper in our model steel. From the SCM microstructure, it is observed that the area fraction of DP regions decreases with the increase of copper additions, increasing the copper content to 1.5% results in a complete suppression of the DP reaction. Because only Cp was found in the 1.5 copper steel, we now compare the continuous precipitation in 0 copper and 1.5 copper steel. The atom probe thermography was performed in the Cp regions of the 0 copper and 1.5 copper steels in the 3 aging conditions. And we can see although spherical or nickel-aluminum nanoparticles were detected in both alloys, the particles exhibit considerable differences in the particle size and volume fraction. It is apparent that copper addition accelerates and promotes the continuous nickel-aluminum precipitation. The Cp reaction was accelerated by the copper addition. Well, to deeply understand the underlying mechanisms of the effects of copper on the nickel-aluminum precipitates, we calculated the proximity histograms. It is clear to see that in the copper-added steel, the copper partitions to the nickel-aluminum particles. Well, from the atom maps of the center of some represent nickel-aluminum particles in all conditions, we can clearly see that the copper atoms, the red atoms, are partitioned into the nickel-aluminum precipitates. So, from the above results, we demonstrate that copper is effective in not only promoting the continuous nickel-aluminum precipitation, but also in suppressing the discontinuous precipitation at green boundaries. Well, for the mechanisms of copper-induced continuous precipitation acceleration, we do some first principles calculation to see the effects of copper on the acceleration of the Cp acceleration. Well, the results show that the formation energy of nickel-aluminum pairs in the copper conditioning supercells are lower than that of nickel-aluminum pairs in copper-free supercells. This suggests that copper enhances the interaction between nickel and aluminum pairs. and thereby increases the chemical driving force for nickel-aluminum precipitation. For the mechanisms of copper-induced DP suppression, the precipitation behavior can be schematically illustrated in this figure. Left side is the V-shaped discontinuous precipitate, and the alpha prime phase with the higher supersaturation, and the right side is a continuous spherical nickel-aluminum particles, and the alpha prime phase with a lower supersaturation. We calculated the nickel concentrations in the matrix of the DP and CP of the DP and CP regions across the migrating group boundary. We found that the nickel concentration in the CP regions is apparently higher than that in the DP regions. Thus, we concluded that a concentration difference of those across the migrating group boundary provides the chemical driving force for the DP groups. Well, based on this theory, we calculated the solute concentrations in the CP and DP regions of the zero copper steel, and that in the CP regions is 1.5 copper steel. The CP reaction of the 1.5 copper steel consumes the supersaturated matter more rapidly than that of the zero copper steel, which leads to a considerable decrease in nickel and aluminum supersaturation in the early stages of precipitation. Then we calculated the chemical driving force of the BP reaction via this equation. We found that the chemical driving force of the BP reaction is dramatically decreased by evaporation. So we now analyze the effect of copper segregation at group boundaries on the BP reaction. At the early aging stages, we can see that copper segregated at group boundaries after aging for 2 hours. Only spherical nickel aluminum copper precipitate instead of the rod-like discontinuous precipitate were formed in the group boundary region, which further confirms the suppression of the DP reaction. So, in summary, the precipitation mechanisms in copper-free steel and copper-modified steel as summarized in this figure. On the one hand, the copper-induced acceleration of the CP reaction, which significantly reduces the chemical driving force for the DP group. And on the other hand, the copper-induced reduction of the copper segregation at the group boundary can directly suppress the DP groups. Furthermore, we checked the mechanical properties. The Vickers harness and the tensile test were performed to investigate the copper effects on the mechanical properties. As we can see from these two figures, the continuous precipitation in copper modified steel shows a higher returning response put over aging resistance, and the yield strength was improved by copper addition from 900 megapascal to 1,400 megapascal. And the activity was not sacrificed with increased yield strength. So here displays our conclusions. The first is nickel aluminum precipitation in fluoritic state occurs in two modes, namely the continuous precipitation and discontinuous precipitation. And the suppression of the continuous precipitation can be attributed mainly to the acceleration of CP formations in the copper partitioning, and on the other hand, copper segregation and group boundaries can directly suppress the DP reaction. And we also obtained um, a high space field with high yield strength and good activity. Okay, that's all.